This video is about the aromatic chemistry of benzene and the reactions of benzene. It's in 3.3.10. The first section is about bonding, and we're just going to discuss two things. First thing is the nature of the bonding in benzene, and secondly the evidence that this type of bonding exists. So first, Kekule, the chemist, came up with the idea that benzene was a cyclic structure. And it was thought that it was a series of double and single carbon-carbon bonds, a bit like in cyclohexane, and that is cyclic. There's double, single, double, single, 6 carbons, 6 hydrogens for the molecular formula of C6H6. However, due to evidence that's been collected, the modern understanding of this structure is that it's made of sort of 1.5 bonds, so no longer double, single, double, single, double, single, but 1.5, 1.5, and 6 of them in a group. And so the skeletal formula we can see perhaps a bit more clearly is that you can see the single double pattern, but in the delocalized structure the bonds are the electrons within the bonds are equally shared around the carbons, so there's no double single cycle. And the evidence that supports this is that, first of all, if you think about the structure in the Kekule structure, you think, well, they would have a longer bond for the single and a short bond for the double, but that's not true. Evidence shows that they're actually all of the same length. Second thing you might think about with this structure is that it's going to undergo electrophilic addition like the alkenes do, but that doesn't happen. It takes much more harsher conditions for the benzene to undergo with bromine. So that's the second piece of evidence. The third piece of evidence is about the addition of hydrogen to this molecule, and when hydrogen is added to the theoretical Kekule structure, it would be minus 360 kilojoules per mole. But with the it's found to be, so 360, it's found to be though minus 208 kilojoules per mole. So that's more endothermic. It's not as exothermic as we'd expect. And this has been described as being down to something called delocalization energy. So the electrons shared in this benzene ring cause extra stability, and it requires more energy, i.e. 152 kilojoules per mole of energy to break down this structure. So that's the third piece of evidence. Just talk about this evidence a bit more, this third piece, and what is delocalization energy? How does it happen? First, a recap of alkenes from year 1 chemistry. So what alkenes have, they have these p orbitals, and to form the second bond of the CC double bond, that the p electrons overlap to form this pi bond, and a pi bond exists above and below the other bond. This is called a sigma bond between the two carbons. Now when we look at benzene and how that works, if benzene's got 6 carbons in it, so what happens is these p orbitals, they overlap, and they overlap around the whole of the molecule, and so this leads to extra stability. If bromine, for example, wanted to break this structure down, it would have to break some of it but not all of it, and so that would make it more difficult. And so this is the delocalization stability that's accounted for in the third piece of evidence. Some of the properties and reactions of benzene. Firstly, that benzene is a planar structure. If you imagine it's got 120 degrees around its carbon-carbon bonds, so it is planar, whereas hexane is tetrahedral. So this affects the way that the molecules can approach each other, and the benzene molecules can approach, therefore there's a more effective contact between the molecules, and that leads to a higher melting point. because they have stronger van der Waals because they can approach each other much more effectively. The second property of benzene is insoluble in water. Benzene is nonpolar. It's just CC bonds, CCH bonds. There's very little difference in electron leading to van der Waals. Water is polar. So because they have different intermolecular forces, they don't dissolve in each other. Just a final thing is that, like other hydrocarbons, benzene does burn. It burns with a smoky flame. And there's the balanced equation for the complete combustion of benzene. But as it's a smoky flame, which uses carbon, there's a large amount of soot that's produced, so alternative reactions could be written. The second part of benzene is to think about electrophilic substitution reactions. The acronym I use to learn this is BEST. So benzene, electrophilic, and then substitution. The ST stands for substitution. So what I'm going to show you briefly is how it works, the overview of something of the substitution reaction, and how it works. The reason for substitution talked about briefly already regarding the delocalization stability, nitration of benzene, and the Friedel-Crafts acylation. They're two examples of electrophilic substitution reaction you're going to learn about. So benzene does not undergo electrophilic substitution reaction. Electrophilic addition reactions because of the extra delocalization stability. So what happens is atoms are substituted instead. So briefly show you how it works. So we have the benzene ring here. The electron-rich area within the benzene is attracted towards a very powerful electrophile. It needs to be powerful to draw the electron pair to the E+. From this, E+ stands for electrophile, to draw it from the delocalized electrons. But what needs to happen is this. There's an H on each corner here. Remember, it's C6H6. So this H here, which I'm showing there, the bond breaks so that the delocalization stability returns, and it releases this H+. So what I'm going to show you now is how this reaction takes place with the nitration of benzene and the Friedel-Crafts acylation. So reaction number 1 is about nitration of benzene. Now, first of all, background, how does it work? Well, we have conc nitric acid as a reagent, supplies the NO2+, and then conc H2SO4 is the catalyst for the reaction. So what happens is the sulfuric acid reacts to nitric acid, and the H2SO4 behaves as the acid, donates a proton, and the HNO3 behaves as a base. In the second step, the H2NO3 plus ion, it turns into NO2 plus, so forms this very powerful electrophile, and water is the byproduct of that reaction. And then this electrophile reacts in the same way as I showed you earlier. So benzene, electron-rich benzene, the electrons go from the circle, from the electrons in the circle to the NO2 plus. To reform the stable benzene ring, the bond between the C and the H bond breaks, and it releases and the H is released. The NO2 stays intact on the benzene. And so the product there is nitrobenzene, as H plus is the byproduct. The overall balanced equation for this, so benzene reacts with nitric acid, and then it's nitrobenzene and water. The water was created here. The H plus from the reaction, so this H plus here, can reform the catalyst and form HSO4 minus. Reacts with HSO4 minus, forming H2SO4. Just go into this small diagram here. This is the why we may carry out nitration. So in explosive, in mining, for example, trinitrotoluene (TNT). So it's trinitrotoluene, and toluene is methylbenzene, so that methyl group there. And this is 2,4,6-dinitrophenol. This is just another example of groups like this where they can introduce more than one nitro group into a structure. 2,4,6-trinitrophenol is another explosive. The second reaction I'm going to talk to you about is the electrophilic substitution reaction of benzene with to introduce an acyl group. An acyl group is the introduction of a carbonyl group. So what happens here is we heat under reflux with an acyl halide molecule, so for example ethanoyl chloride, and it reacts with aluminium halide as the catalyst. And if it's a chloride, it will be an aluminium chloride catalyst. So the ethanol chloride reacts with aluminium chloride and forms a negative ion, tetrachlorido aluminium or aluminate ion, and the ethanoyl ion is the byproduct of that reaction. This is the electrophile, and the electrophile here reacts with benzene. So again, the electron-rich region of the benzene moves towards the C+, and then in the second stage we need to reform the delocalization of the electrons. So the bond breaks between the carbon and the hydrogen, and H+ is a byproduct. And now we've introduced this carbonyl group, the acyl group, into the molecule, and this is called phenyl ethanone. Phenyl is often used as a side group, a bit like methyl or ethyl. When we have a benzene, we sometimes use that term phenyl, as written here, phenyl ethanone. The catalyst can reform, so H+ as a byproduct can react with the aluminium tetrachlorido aluminate ion and can reform aluminium trichloride and HCl as a byproduct. And there's the overall reaction. On this slide here you see some names. You may have a little bit of time to try and draw those molecules, and the answers are written underneath, and the rest of the answers are written here.